$80 camping stove can fail in minutes. Wind pushes the flame sideways and drains heat. Cold air thickens fuel and lowers pressure. An empty canister ends everything instantly. Historical records and reconstructions show medieval fire systems that burned for more than 18 hours straight without maintenance, valves or moving parts. Modern camping stoves feel reliable because they look engineered. Shiny metal, precise knobs, controlled output. You turn a dial and fire appears. That visual control creates trust, but only under ideal conditions. Once the surroundings stop cooperating, the weaknesses surface. The first weakness is dependence. A modern stove depends on pressurized fuel, sealed components, and stable airflow. Every part relies on another part working perfectly. If fuel pressure drops, the flame weakens. If wind increases, heat disappears. If cold interferes with flow, combustion stalls. One failure point shuts the entire system down. The second weakness is exposure. Camping stoves produce flame but do almost nothing to protect it. Thin metal sheds heat instead of holding it. Open burners allow wind to strip warmth faster than it can be replaced. The user becomes part of the system, constantly adjusting and correcting. The fire survives only as long as it is actively managed. This design is not an accident. Modern stoves are optimized for portability and speed. Thin materials reduce weight. Pressurized fuel delivers instant ignition. Compact designs pack easily. These choices make sense for convenience, but they sacrifice endurance. Heat is generated quickly and lost just as fast. Nothing is stored. Nothing is stabilized. Medieval fire was built around sustained heat. Fire was not something you constantly watched and corrected. It was something you built to last. Instead of producing energy continuously, medieval systems focused on trapping, protecting, and slowly releasing it. Modern stoves fail not because they are poorly made, but because they are designed for perfect scenarios. Medieval fire systems were designed for imperfect ones. Wind, cold, and neglect were assumed, not treated as exceptions. A gadget optimized for convenience will always struggle against conditions it was never meant to control. The biggest mistake we make when we think about medieval fire is assuming they were chasing flames. They weren't. Flame was incidental. What they cared about was heat that stayed put. For medieval people, fire was infrastructure. It heated rooms, cooked food, dried clothes, preserved tools, and kept families alive through long nights. A fire that flared brightly and died quickly was useless. The goal was a steady, predictable release of warmth that could survive wind, cold, and inattention, that required thinking in systems. The first piece of that system was thermal mass. Medieval fires were surrounded by stone, packed earth, brick, or clay. These materials absorbed heat slowly and released it even more slowly. Once warm, they acted like batteries. The fire could weaken or even drop to embers, and the space would remain warm for hours. Modern camping stoves isolate the flame from anything that could store heat. Thin metal heats fast and cools instantly. The moment the flame weakens, the warmth vanishes. Medieval builders anchored fire to heavy materials that remembered heat, long after the flames changed. The second piece was airflow direction. Medieval fires were shaped by walls, pits, reflectors, and openings that guided air, instead of fighting it. Wind was not treated as an enemy to block completely, but as a force to be redirected. Air entered where it was useful, and exited where it was safe. Combustion depends on oxygen, but uncontrolled airflow strips heat faster than fire can generate it. Medieval fire systems balanced that equation: enough air to keep embers alive, not so much that heat was torn away. The fire stayed calm. Fuel pacing was another concept modern stoves largely ignore. Medieval fires were not fed all at once. Fuel was layered, sized, and spaced to burn gradually. Dense logs, charcoal, or packed organic material limited how fast energy could escape. The fire was designed to slow itself down. Modern stoves deliver fuel continuously at a fixed rate. Turn the valve, get flame. Turn it off, get nothing. There is no memory in the system. Medieval fire had memory because fuel release was governed by structure, not pressure. Medieval fires were protected, not hidden, but shielded. Trenches, stone backs, earth banks, and simple windbreaks prevented exposure from every direction. Fire was treated as something that needed boundaries. Within those boundaries, it could be trusted to last. None of this was romantic or mystical. It was practical. People learned quickly that fire without structure demanded constant attention, while fire with structure could be left alone. Over generations, that knowledge hardened into habit. Calling medieval fire primitive misses the point. It was less flashy, but more deliberate. It sacrificed instant ignition for stability. It traded control knobs for geometry and materials. The result was a fire that didn't need babysitting to survive the night. When you understand fire as a system, heat storage, airflow control, fuel pacing, and protection, the endurance makes sense. When medieval fire lasted through the night, it wasn't because of luck. It was because each fire was built to remove a failure point before it could cause trouble. Over centuries, a handful of techniques survived precisely because they worked in bad conditions. Each one looks simple, each one quietly solves a problem that modern stoves struggle with. The first was the stone-banked hearth. Fire was rarely left naked. Stones were stacked tightly around the burn area, sometimes on 3 sides, sometimes in a full ring. Stone absorbs heat slowly and releases it slowly. Once warmed, it reduces temperature swings. Gusts don't matter as much because the heat is stored in mass, not suspended in flame. Even when the fire drops to embers, the hearth continues to radiate warmth. A modern stove has no such buffer. When the flame weakens, the heat disappears instantly. The second was the reflector fire. Instead of placing fire in the open, medieval builders positioned a wall of stone or packed earth behind it. Heat that would normally escape backward was reflected forward, doubling its usefulness without increasing fuel. This wasn't about making the fire bigger, it was about directing energy. Modern burners radiate heat in all directions and lose most of it to the air. Reflectors turn wasted heat into working heat. The third technique was the trench fire, dug slightly below ground level. Earth acts as insulation. By lowering the fire, medieval builders shielded it from wind while stabilizing temperature. The surrounding soil absorbed heat during peak burn and released it slowly afterward. This reduced flame volatility and protected embers from sudden exposure. Modern stoves elevate the flame, placing it directly in the path of moving air. Trenches did the opposite. The fourth was ember banking, one of the most misunderstood methods. Medieval fires were often designed to transition intentionally from flame to embers. At night, hot coals were covered with ash or soil to restrict oxygen. Combustion slowed dramatically, but heat remained trapped. By morning, uncovering the embers brought the fire back to life with minimal effort. This method eliminated the need for constant fuel or relighting. Modern stoves cannot bank heat this way, because once fuel flow stops, the system goes cold. The fifth technique was earth insulation around the firebase. Clay, ash, and compacted soil were used to seal gaps and reduce heat loss into the ground. This mattered because bare ground acts as a heat sink, draining warmth away. Insulation flipped that relationship. Heat stayed where it was needed. Modern stoves sit on thin legs or metal bases that conduct heat away instead of retaining it. The sixth was wind geometry. Medieval fires were shaped so that wind fed combustion without stripping heat. Openings were angled, walls were placed asymmetrically, air entered low and exited high, creating a gentle draft that supported embers instead of tearing them apart. Wind became a controlled input, not a random threat. Modern stoves rely on external shields because their geometry does nothing to manage airflow internally. The seventh technique was slow feed fuel logic. Fuel was selected and arranged to burn at a predictable pace. Dense woods, charcoal, and layered construction limited how fast energy could escape. The structure decided the burn rate, not a valve. This removed human error. Once built correctly, the fire regulated itself. Modern stoves push fuel continuously at a fixed rate, requiring constant adjustment as conditions change. Taken together, these techniques share one principle. They do not fight the environment, they design around it. Heat is stored instead of chased. Air is guided instead of blocked. Fuel is paced instead of forced. Each method removes a dependency that could fail. These fires outlast modern stoves because they don't rely on pressure, precision parts, or perfect weather. They rely on mass, geometry, and time. The flame becomes secondary, the system does the work. Modern fire gear doesn't fail because engineers forgot how fire works. It fails because the goal changed. Fire tools were redesigned to move faster, weigh less, and ship cheaper. Endurance fell off the list. Start with materials. Modern stoves are built from thin metals that heat quickly and cool just as fast. That makes them light and responsive, but it also makes them fragile in real conditions. Heat has nowhere to stay. The moment wind rises or fuel delivery stutters, the system loses stability. Medieval fire systems leaned on mass stone, earth, brick, because mass smooths extremes, thin metal amplifies them, pressurization creates another vulnerability. A camping stove depends on stored energy inside a canister. Pressure pushes fuel through tiny passages to create flame. It's elegant, compact, and precise. It's also unforgiving. Cold lowers pressure. Minor leaks stop flow. Valves clog. Regulators ice up. When pressure drops, the entire system collapses at once. Medieval fires had no pressure to lose. Combustion slowed or sped up, but it didn't vanish. Fuel dependency is the next trade. Modern stoves burn one specific input in one specific way. When that input runs out, the fire ends completely. Medieval systems treated fuel as a variable, not a lifeline. Different woods, charcoal, peat, even agricultural waste could be layered and paced. Manufacturing priorities finish the picture. Modern gear is designed to be produced at scale, assembled quickly, and replaced easily. That means fewer parts that take time to shape, fewer materials that add weight, fewer steps that require skill. The result is consistency, not resilience. You get a tool that works the same way every time until conditions change. Medieval fire systems came from the opposite pressure. Time was abundant. Labour was local. Failure was costly. A fire that died in the night meant cold, hunger, or danger. Designs evolved to tolerate mistakes and bad weather because they had to. Stability wasn't a feature. It was survival. Modern gear often feels impressive in demonstrations and disappointing in use. It performs best in controlled scenarios. Medieval systems performed best when things went wrong. The contrast is not about better or worse engineering. It's about what was optimized. Modern tools optimize for convenience, portability, and speed. Medieval systems optimized for continuity. Endurance doesn't come from making a fire hotter, it comes from making it stable. Modern gear treats heat as something you generate on demand, then lose the moment conditions change. Medieval fire treated heat as something you store, shape, and protect. A stable fire doesn't panic when the wind shifts. It doesn't collapse when attention drifts. It doesn't demand perfect inputs at the right moment. It keeps working because its strength isn't concentrated in one fragile point. It's distributed across mass, geometry, and time. That logic still works today. You don't have to live like a medieval peasant to use it. You don't need to reject modern tools or romanticize hardship. You simply stop expecting a gadget to do the work of a system. When you add mass around heat, guide air instead of fighting it, pace fuel instead of forcing it, endurance appears. Medieval fire techniques resurface wherever reliability matters most, in off-grid cabins, in long winter camps, in emergency situations where fuel is limited and attention is stretched thin. The same principles keep showing up because physics hasn't changed. Heat still behaves the same way. Air still strips energy when it's unmanaged. Mass still smooths extremes. Modern stoves can still be useful. They're fast, they're convenient, they're precise, but they're best understood as ignition tools, not endurance solutions. When conditions are easy, they shine. When conditions turn hostile, they reveal what they were never designed to do. Medieval fire systems filled that gap by default. They assumed the night would be long, the wind unpredictable, and human focus imperfect. Instead of demanding constant correction, they absorbed mistakes and kept going. Many modern tools fail for the same reason. They work brilliantly when everything behaves and fall apart when it doesn't. Older systems that look inefficient on paper keep functioning because they were built around reality, not ideal conditions. Fire just makes the pattern visible. The medieval builders weren't smarter. They were constrained differently. They optimized for continuity because they had to. We optimized for speed because we could. Neither choice was wrong, but each came with consequences.